Lesson: Theoretical limits of NLP in cybersecurity. Natural language processing has emerged as a pivotal technology in the realm of cybersecurity, offering a suite of tools and techniques that enhance the detection, analysis, and mitigation of cyber threats. Despite its significant contributions, NLP is bound by theoretical limits that present challenges to its application in cybersecurity. Understanding these limits is crucial for developing realistic expectations and advancing the technology in ways that address its current shortcomings. NLP's application in cybersecurity spans various domains, including threat intelligence, anomaly detection, and automated response systems. For instance, NLP can process large volumes of unstructured text data from threat reports, social media, and dark web forums to identify potential threats. However, the complexity of natural language poses significant hurdles. Language is inherently ambiguous, context-dependent, and constantly evolving, which complicates the task of accurate threat detection. One major theoretical limit of NLP in cybersecurity is the challenge of semantic understanding. While NLP models can be trained to recognize patterns and keywords associated with cyber threats, they often struggle with deeper comprehension. This limitation is evident in the inability of models to fully grasp intent and subtleties in language, leading to potential false positives or negatives in threat detection. Moreover, the effectiveness of NLP in cybersecurity is heavily dependent on the quality and quantity of training data. The security domain is characterized by highly specific jargon and rapidly changing threat landscapes, which necessitates continuous updates to training datasets. However, obtaining labeled data for training NLP models is a labor-intensive and time-consuming process. The scarcity of high-quality, annotated data can hinder the performance of NLP systems, particularly in detecting novel or sophisticated threats. For example, sophisticated phishing attacks that employ nuanced language and social engineering tactics may evade detection due to the model's lack of exposure to similar instances during training. Another theoretical limit relates to the adversarial nature of cybersecurity. Attackers continuously adapt their strategies to evade detection, often exploiting the very algorithms designed to thwart them. This adversarial environment exacerbates the challenge for NLP models, which can be manipulated through adversarial attacks. For instance, slight modifications in text, such as typos or the use of synonyms, can deceive NLP models into misclassifying malicious content as benign. This vulnerability underscores the need for robust adversarial training and the development of models resilient to such manipulations. The interpretability of NLP models also presents a significant theoretical limit. Many state-of-the-art NLP models, such as deep neural networks, operate as black boxes, offering little insight into their decision-making processes. This lack of transparency can be problematic in cybersecurity, where understanding the rationale behind a model's prediction is crucial for trust and compliance. Security analysts need to comprehend why a particular threat was flagged to validate and act upon the alerts effectively. The opacity of current NLP models can hinder this process, leading to potential oversight or mistrust in automated systems. Furthermore, the dynamic nature of language and the context-specific nuances in cybersecurity communications pose additional challenges. Cyber threats often involve domain-specific terminologies and slang that evolve rapidly. NLP models must continually adapt to these changes to maintain their effectiveness. However, the dynamic adaptation of models is a complex task that involves retraining with updated datasets, which may not always be feasible in real-time scenarios. This lag in adaptation can result in outdated models that fail to recognize emerging threats. Despite these theoretical limits, ongoing advancements in NLP research offer potential solutions to mitigate some of these challenges. Techniques such as transfer learning, where models pre-trained on large corpora are fine-tuned on specific cybersecurity datasets, have shown promise in improving model performance with limited data. Additionally, the development of explainable AI aims to address the interpretability issue, providing insights into model decisions and enhancing trust in automated systems. Adversarial training methods are also being explored to enhance the robustness of NLP models against manipulation by attackers. In conclusion, While NLP holds significant promise for enhancing cybersecurity through improved threat detection, analysis, and response, it is constrained by several theoretical limits. These include challenges in semantic understanding, data dependency, adversarial manipulation, model interpretability, and the dynamic nature of language. Addressing these limits requires a concerted effort in research and development to create more resilient, adaptable, and transparent NLP models. By recognizing and tackling these challenges, the cybersecurity community can better harness the power of NLP to protect against evolving cyber threats.